Now come to the next point, induced electric field. So, as we know, according to Faraday's, whenever there is change in flux, from Faraday's law, as we know, induced EMF E is given as d phi by dt. So, now if we are keeping the area constant and we are changing the magnetic field. So, suppose area is here constant and magnetic field here vary, then also there is a change in flux. So, it has been found that whenever there is a change in the magnetic field, then EMF develop because of the induced electric field. So, we can write here, whenever there is a change in magnetic field with the time, whenever there is change in magnetic field with the time, or we can say time varying magnetic field, time varying magnetic field. So, whenever there is change in magnetic field with the time, it produces electric field, that field is known as induced electric field. So, that induced electric field follows the Lenz law as well as Faraday's law, follows the Lenz and Faraday's law. So, if a loop is kept, if a conducting loop is kept in time varying magnetic field, if a conducting loop is kept in time varying magnetic field, it has been found that there is a current, in that loop, and direction of current follows the Lenz law. So, it has been concluded that loop was at rest, then which force is responsible for motion of electrons, then which force is responsible for motion of electrons which constitute current, which constitutes current. So it has been concluded, that there must be a electric field which is responsible for that current, that current. From these observation it has been concluded. From these observation it has been concluded that a time varying magnetic field produces induced electric field. This is the meaning of whole statement. So whenever there is a time varying magnetic field, it means when the magnetic field vary with the time, it always produces a induced electric field. So once again we can say, whenever there is a change in magnetic field with time or time varying magnetic field, it produces electric field. That field is known as induced electric field. So what has been observed, that induced electric field follows the Lenz and Faraday's law. So what has been observed, if a conducting loop is kept in the time varying magnetic field, it has been found that there is a current in that loop, and that current and direction of that current follows Lenz's law. It means the direction of current will be such that it opposes the change in the flux. Here flux is changing because of the time varying magnetic field. So it will opposes the variation of magnetic field. It means magnetic field if increases, it will try to decrease the field, and if the field is decreases, then it will increase the field. Then it has been concluded that loop was at rest. So what has been observed, although loop is at rest, then which force is responsible for the motion of electron which constitute current? Because in a current, a magnetic force always act when the charge is moving, but the conductor is at rest, loop is at rest, so there is no chance of magnetic force. Then which force is responsible? So it has been concluded that there must be electric field which is responsible for that current. So from these observation it has been finally concluded that a time varying magnetic field always produces induced electric field. So see, if we are taking just so one important point is that the presence of conducting loop is not the criteria of induced electric field. Presence of your conducting loop is just for observation. Although either loop is present or not, the electric field will be always there. Okay. So now see the just one point here, if we want to say. So as we found induced electric field, so whenever there is a time varying magnetic field, it produces induced electric field. So we can have some region of time varying magnetic field like this. Suppose this is your magnetic field, and if we are considering the dB by dt is greater than 0, it means the magnetic field here increasing with respect to time. So, what has been observed? Suppose, see, the presence of loop does not indicate the induced electric field. Now, if suppose a conducting loop is kept, the presence of conducting loop is just for a verification point of view. So, what has been found? Suppose this is a loop has been kept here and magnetic field here vary. So, flux associated with this loop will increases, because magnetic field here increasing with the time. The flux associated with this loop here increases. So, because of the increase in the flux, according to Lenz's law, current will be in such a direction, it will try to decrease the flux. So, by decreasing the magnetic field your inward direction, the magnetic field can be decreased by flowing the current in the anti-clockwise direction. So, now current direction your anti-clockwise. So, this is the direction of current. So, from current direction we can conclude electrons are moving here in this direction. So, motion of electron is like this. So, electron is always moving opposite direction of electric field, because electron is negatively charged. From here it can be concluded electric field is here acting in the radial in the tangential direction, and direction of electric field can be said in the direction of current. So, this is the meaning of induced electric field. Now, from here we can conclude here. Suppose electron is there and let r is the radius of a loop. So, what can be said here? Given force on electron. So, force on electron F is equal to your E into E, and that force is acting in the direction of electric field, opposite direction of electric field. And another point here, the electric field your radial direction. So, work done on electron in one cycle, or in one cycle means one round, that is your E into E. This is the force into 2 pi r, that is the work done. So, according to definition of EMF E. So, EMF defined as work done per unit charge. The EMF is defined as work done per unit charge. So, EMF can be written as W by E, and W is here E into 2 pi r by E, and this further written as E into 2 pi r, and 2 pi r we can write here E dot 2 pi r means dl, and this is for a complete loop in this manner. Or we can say here that this is your E dot dr or dl. This is the meaning of EMF. So, as per the Faraday's law, induced EMF E is equal to rate of change of flux d phi by dt, which can be written as E dot dr. This is the conclusion we can get from here. E is equal to d phi by dt E dot dr. So, this is the main point here. Now, write down the certain properties of this induced electric field. As we have found, induced EMF E is rate of change of flux, as well as it can be defined as E dot dl or dr. So, where E is the induced electric field. E is induced electric field. So, now write down the properties of field. Properties of induced electric field. First point, induced electric field is non-conservative by nature. It is non-conservative. It is non-conservative field. So, we can write that there is no relation between electric field produced by charged particle and electric field due to time varying field, magnetic field. Second point, electric lines of forces due to induced electric field always makes a closed curve, just like lines of forces by the magnet, just like magnetic lines of forces. It means electric lines of forces due to induced electric field always makes a closed curve. Third point, since induced field is non-conservative, so potential due to this field, due to this field is not defined. Potential due to this field is not defined, because potential is defined only for conservative field. So, these are the main points related to induced electric field. So, first thing is that it is non-conservative field and there is no relation between electric field produced by charged particle and electric field due to time varying magnetic field. Second thing, electric lines of forces due to induced electric field always makes a closed curve, just like a magnetic lines of forces. Third point, since induced field is non-conservative, so potential due to this field is not defined. See how we are calculating the induced electric field due to cylindrical time varying magnetic field region. Now see the calculation of induced electric field due to cylindrical region of time varying magnetic field. Cylindrical region of time varying magnetic field. So this is a very important point here. So what we are doing here, we are considering a cylindrical region of time varying magnetic field. Let this is the region in which magnetic field is your vary. Let R is the radius of that region. So first thing is that we should be very much clear about कि whenever time varying magnetic field present in the space, it produces electric field. Either that point is within the field or outside the field. So here this is the cylindrical region of time varying magnetic field, and let dB by dt is here greater than 0. It means we are assuming that the magnetic field here increasing with the time. Now there are 2-3 points here. First we can say outside of that region. Now electric field outside the region of magnetic field, outside the region of magnetic field, it means let R is greater than R. It means I am looking the somewhere, let point P here. So this is the point or on this region. So what we will do, just to assume if a conducting ring is placed here, conducting ring of radius R has been placed, then what could be the direction of current on that ring? So what I observe, if a conducting ring is placed here, inside the ring flux is your increasing because of magnetic field your increasing. So what current direction will be such that it will try to decrease the flux. Flux can be decreased by decreasing the magnetic field this here. The magnetic field should be your outward direction. For outward direction, current in the loop will be your in anti-clockwise, and direction of current and direction of electric field will be in the same sense. So electric field will be your in this direction E. So according to Faraday's law, phi is written as E dot dl, that is your d phi by dt, or which is your induced EMF, or we can say induced EMF E. So here rate of change in flux, flux is changing because of the area changes, but flux changing only in this part. There is no field here, there is no change in the flux for this part. So this part have radius r. So d phi by dt written as pi r square into dB by dt is equal to your E dot dr. So here electric field in this direction, we are also moving in the same direction. So, angle between electric field and dl vector will be a 0. So, cos 0 will be your 1. So, E and then dl, and dl means that sign indicate for a complete loop. For a complete loop, total length will be a 2 pi r. So, this is nothing E into 2 pi r. So, we can write here E is equal to your, better we can say E outside point. E outside we can write this pi and pi cancel here. So, r square by 2r dB by dt. So, this is the electric field or induced electric field outside the cylindrical region of magnetic field. Similarly, if we are having second case, electric field inside the region of magnetic field. See the next case. So, this relation we have to remember. So, for outside point, we can write the electric field relation here, r square by 2r dB by dt. That relation will be very helpful for solving different type of questions here. In the second part, induced electric field, inside the cylindrical region of magnetic field, inside the cylindrical region of time varying field, time varying magnetic field. So, it means if we are having, this is the cylindrical region of time varying magnetic field. So, magnetic field here vary only in this region, and we want to find the electric field at any point inside this. So, these are the direction of electric field. Let r is the radius. Again same thing here, I am assuming dB by dt is greater than 0. That assumption only just to check the direction of induced electric field. Now, if I am considering any point, suppose here P here, which are distance here r from the conductor. So, here the meaning is that r is your less than capital R. So, again if I am assuming a loop of radius r kept like this, a conducting loop of radius r kept like this, so which type of current or in which sense the current will establish? See, if I am considering this radius r, so what we will observe, as the flux magnetic field here increases, the current will be such that it decreases. Again, current here anti-clockwise sense, the anti-clockwise current sense give you anti-clockwise direction of induced field like this. This is the direction of induced electric field. Because of this electric field, that is called direction of electric field. Now, we can use the again flux or d phi by dt is equal to your E dot dl again. Now, rate of change of flux. The flux is changing only in this, within this area that have radius small r. So, that can be written as pi r square dB by dt, that is equal to your E dot dl. So, E here inside point, so I can write E inside and then dl. Here also angle between the electric field and our direction of motion are your same. So, the cos theta will be here your 1. So, this is nothing E inside into 2 2 pi r, which is equal to your pi r square dB by dt. So, we found here E inside is equal to your r by 2 into dB by dt. This is the electric field inside this. So, what I observe here from this out that expression and from here. So, E outside, what has been observed? E outside your inversely proportional to R, while E inside is your directly proportional to R. So, we can write here E inside relation, that is your R by 2 into dB by dt into dB by dt. So, if we want to make a complete graph, how the electric field vary with the distance. So, we can make a graph like this. Up to the capital R, it will linearly vary, and after that it is your rectangular hyperbolic. So, this is the variation of induced electric field with a position from the axis of the cylindrical region of time varying magnetic field. So, these two are very important result, this and this. So, most of the problem are based on in these two results whenever we are talking about time varying induced electric field. Now, see few example based on this. Now, see this example 1. In this example, it is given a time varying magnetic field B is exerting into the plane of this board, and magnetic field vary according to the relation 2t cube minus 4t square plus 0.8 Tesla. And this is the cylindrical region of magnetic field of radius r, and there are 2 points in the space. One is your P1, another your P2. Point P1 is inside the cylindrical region, while point P2 is your outside the cylindrical region of time varying field. And the relation between R2 and R is given. R2 is equal to 2R, which is equal to 5 centimeter. Now, see what is the question here. Our question is that force on electron located at P2. Located at P2 means at point P2 at t is equal to 2 seconds. This is the first part of the problem. And second question is that find the direction of electric field at P1 when t is this, and location and position of the point P1 is your 0.02 meter from the center of this. So, this is the problem here. Now, see how to do the question here. First thing, if I am talking about the first part, the first part, force on the electron. Force on electron is given as charge on electron into electric field. So, first we would like to calculate electric field. So, see electric field, and this point P2 is outside point. So, in outside point we have derived the result of electric field, which is your R square by 2R dB by dt. This is the electric field relation for outside point. So, electric field at point P2, if I am writing at point P2, R square and distance of point P2 here 2R2 like this. So, after knowing the electric field, substitute the value of electric field here, you will get the force. Another point comes, what is the direction of force also. See, first we will calculate the dB by dt value. See, dB by dt. Differentiating this one, so we will get 6 t square minus 8t, and at this moment at 2 seconds, dB by dt at t is equal to 2. So, that gives us 6 into 4 minus 16, that is your 8. So dV by dt comes here positive. Positive dV by dt indicating here magnetic field here increases. So if I am assuming a loop here, so magnetic field here increasing. So to decrease the magnetic field, induced current should be your in anti-clockwise direction. So direction of electric field will be your tangential to this loop or tangential to this circle like this. So if electron is kept here, so force on electron here in this direction. Why? Because the electric field here negatively charged. The force on electron will be in this direction, and we can calculate the magnetic field here. So just put the value of dV by dt here. So see, electric field at this point r square, r value given here 2.5. So 5 by 2 is square, and this is centimeter, convert into meter, minus 4 divided by 2 r2. R2 your 5 into 10 power minus 2. This is the r square by 2 r2, and dV by dt we are getting 8. So into 8. Now simplify. So this is your 25 into 10 power minus 4 into 8 by 4 into 10 into 10 power minus 2. So this will be here 10 power minus 2 25 into 8 200 into 10 power minus 4 by 40 into 10 power minus 2. So this will be your 5 into 10 power minus 2 volt, we can say volt per meter. This is the electric field. After that, substitute here the force on a charge, force on electron. Just find the magnitude of the charge of the electron, 10 power minus 19 into electric field here 5 10 power minus 2. It become your 8 into 10 to the power minus 21 Newton. This is the force on electron at point P2. This is the first part. Now if we are looking the second part, B part, if I am looking here, and at B what we have to find? We have to find direction and magnitude of electric field at point P1. P1 is your inside point. Inside point, our relation, if we have remember, inside point relation was your R by 2 into dV by dt. So here dV by dt we have to find at t is equal to 3, and R value is given 0.02. So 0.02 by 2 and dV by dt. See, when we are putting dV by dt at 3, dV by dt at t is equal to 3, substitute the value here, t is 3. So 3 square into 6, 9 into 6, 54 minus 8 into 3, 24. This will be your 30. So dV by dt is coming your 30, and that indicate it is also positive, it means increasing. So this is your 30. So finally your answer is your 0.3 volt per meter. This is the induced electric field, and since magnetic field are increasing, so here also if I am making a circle of radius r, so electric field will be tangential, and that have direction to decrease the flux or decrease the effect of magnetic field. So electric field here also radially in anti-clockwise, tangentially in anti-clockwise direction. So this is the answer of B part also. Now come to the another example. Now see the another example. In this question here, a time varying cylindrical region of magnetic field is given. This is the radius r of time varying cylindrical region of magnetic field, and let dB by dt is given here, alpha, where alpha can be said as a positive constant. Alpha is a positive constant. It means in this region only magnetic field will vary. Now, if I am putting a conductor PQ here, if I am putting conductor PQ here, so question is that find induced EMF across the ends of conductor PQ. This is the question here. And length of conductor, suppose it is given here L. Length of conductor here given L, and O is the axis of the conductor, axis of the cylindrical region of time varying magnetic field. Now, then how to calculate here, and what could be the region for induced EMF? Same thing here. As magnetic field vary with the time, so electric field will induce, and that electric field exert a force on a free electrons in a conductor. Because of that force, electrons are polarized. Due to the polarization of charge, electrostatic field also develop, and that electrostatic field and the field or EMF develop because of the time varying field, that will nullify. See like this. If I am looking the time varying magnetic field, so see here, if I am looking the any of the circle like this here, this circle is nothing, it is just like your conductor. If it is placed like this, so magnetic field you are increasing, so here electric field will be your tangentially like this, tangential electric field. Similarly, the lines of forces will pass through the, if I am taking a bigger circle like this, then the electric field lines or electric field lines will be here also like this, like this. So, there is a one component of electric field along this, that component of electric field will exert force on the electrons in this conductor. So, see here, let this point here at r distance from the axis of the loop, and we are moving in this side. So, that is your let x distance, and this is your dx. So, first of all, electric field at this location, see the solution. Electric field at this point, that is the inside point, which is given as r by 2 dB by dt. This is the electric field at the point this. But direction of electric field this, but we have to move here towards Q. So, let this is the angle theta. So, as we know EMF, the EMF across this written as E dot dl. As we are in that side E, we are moving in this side, angle between this theta, value of E is your r by 2 dB by dt dx and cos theta. Now, see, this is your r, this is x, and this angle theta, this is your angle 90 degree, this angle also theta. So, r cos theta is, can be said this length. This can be calculated this is your L by 2, this is your complete radius r. So r cos theta we can get from here by 2, dv by dt also given here, alpha into dx. How much r cos theta? See, r cos theta means this length, this is your capital R, this is your L by 2. So this is equal to your under root of capital R square minus under root of capital R square minus L by 2 whole square by 2 alpha dx. So this is your dE. Now integrate. X we are moving in that side. So from here minus L by 2 to L by 2. When we are looking minus L by 2, point P is there. So EP and L by 2 point Q, EQ. So what has been observed? EQ minus EP, that is equal to your L root over R square minus L square by 4 by 2 into alpha. So what I observe here? EQ minus EP. Since the electric field was in this direction, force on the charged particle, your electrons are your left side. So electron will accumulate here and positive charge at your point Q. That's why Q will be at your higher potential and P is your at lower potential. So this is the induced EMF, and that is equal to the same thing. As electrons are experiencing force in that side, this side, so here charge density or increases. That charge density or produces further electric field from Q to P, and that electric field here due to the charge polarized electrostatic field, and both field will be equal like this. So this is the potential difference or EMF between P and Q point. Now come to the another example. Now see another example. In this example, again we are considering a cylindrical region of time varying magnetic field. And inside the cylindrical region of time varying magnetic field, we are having a conducting loop. And O is the center of that loop. So we can write here A, B, C, D, A is a rectangular conducting loop, placed in cylindrical region of time varying magnetic field as shown in diagram. The one edge of the loop AD is along the or passing through the axis of the cylindrical region. One edge of loop means AD is passing from the from the axis of the cylindrical region the dimension of the loops are rectangular loops are given in diagram. Okay. So, we can assume their dimension. This is let A, this is your B. Okay. Now, the point is this. Now, calculate see first part let induced electric field or induced EMF between A and D. First, induced EMF between points A and D. This is the one part. Second part, we can say find the direction and magnitude of electric field at all labeled points. This is the question here. See, it means we have to find induced EMF between A and D point, as well as we have to find electric field at all labeled point. Labeled point means the point which has been labeled with A, B, C and D. So, first of all, cylindrical region of time varying magnetic field. If I am talking about and dB by dt is your given alpha, and that alpha either we can take let positive constant, alpha is your positive constant. So, when alpha is given a positive constant, then see how to calculate. See, due to the cylindrical region of time varying magnetic field, the electric field will be your concentric circles like this. So, when we are talking about the induced electric field, so induced electric field lines will make concentric circles about center O like this, in that manner. See, so as we know, d phi by dt is given as E dot dl. So, when we are talking about electric field or induced EMF between your EMF E. See, as we are moving from A to D and magnetic field are continuously or increasing, so direction of induced electric field will be your radially anti-clockwise manner like this. This is the direction of induced electric field in this manner. So, what I observe when we are reaching or when we are moving along the line AD, see. So, whatever the magnitude of electric field, first see the direction of electric field and our direction motion. We are moving from A to D or D to A, but as we are moving here, we found on this line direction of electric field always makes a angle 90 degree with our direction. So, angle between E and DL is here always 90 degree. So, dot product of this will be here always 0. So, dot product will be 0. So, what we found here in the first part? In the first part, induced EMF between point A and D will be 0. So, induced EMF between points A and D will be 0. This is the answer of the first part. Now, in the second part, direction and magnitude of electric field at all labeled points. See how to calculate. In the B part, all the label points A, B, C, D, all label points are inside point of the, inside point means those, all those points are lying within the cylindrical region of field. So, inside point formula is already we know R by 2 dB by dt. So, R can be said the radius of that concentric circle which is about O. So, see here, and dB by dt. dB by dt you are increasing because alpha is your positive constant. So, as we have drawn here at point A and D, our concentric circle will be like this, and since magnetic field you are increasing, so our current as well as field direction will be such that this will decrease the magnetic flux. So, electric field will be in this direction like that, and this have radius here B by 2. So, magnitude of electric field at point A is same as at point D, but direction of electric field at A and D will be just opposite to each other. So, radius of that will be this is your equal to your B by 2. So, B by 2 by into 2, B by 4 into alpha. This is the magnitude of electric field at A and D point. Similarly, if I am looking the from O to B and C point, then we have to make a circle of like this. So, here in this case this will be your R, and since this concentric circle have electric field in tangential direction like this, this is tangential direction, the electric field direction will be this, and this will be taken as your R. So, how much is R value? This is your A, this is your B by 2. So, again same thing here, and distance of point B and C is same from point O. So, electric field at B will be equal to electric field at C point. Magnitude is same, but direction at B will be in this direction, direction at C your tangential like this. So, EB is equal to EC, and the radius will be your this value, and which is equal to your A square plus B square by 4. This is R by 2 into dB by dt, dB by dt your alpha. So, this is the magnitude of electric field at B and C, and direction I have shown already here. So, this is the solution of this problem now.